Hey, what's going on YouTube? I think that we're live now. We're also going to go live today on Twitch. We're going to try to dual stream today. So, today is June 25th. The last time that we were in this section was about a month ago, a little bit more than a month ago. And before that was less than a month before that. So these cycles are getting longer until the next time that we come back and revisit a section. So today is chapter 6 on orthogonality from this wonderful book by Fraleigh and Beauregard. And we're going to be talking about projections, the Gram-Schmidt process, orthogonal matrices, the projection matrix, and possibly the method of least squares. I do think that we should try to finally work a problem from section 6.5. For some reason, I haven't been able to get to that section as much. Probably because it's a long chapter. There's a lot of sections here. So I went ahead and copied out some of the problems that we're going to be working today. Let's see. Projections. First, we're going to find orthogonal complements of subspaces. Then we're going to apply the Gram-Schmidt process. Then we're going to use a fact about orthogonality to compute an inverse of a matrix. We're going to compute A inverse utilizing some facts about orthogonality. Then we're going to find a projection matrices, which is a cool topic. And then we're going to look at the method of least squares. If we get to it. If we get to it. I probably should just start there, but you know what? I still don't feel like it. Let's get started. 6.1, projections. I still like to just work all of these sections in order. So hello, if anybody's new for the first time, my name is John. I am relearning mathematics, and I'm doing it in cycles in a way where I start adding new topics after I revisit old topics. So we're doing a bunch of calculus, or we're doing a bunch of linear algebra mostly, but then we start adding some calculus, more linear algebra, more representation theory. But each time that we reset and work chapter 1, 2, 3, 4, 5, etc., all the problems are getting a little bit harder each time, and we're getting into more advanced topics, as well as just adding more chapters, more streams. So it takes a longer time till the next time that we come back, for what it's worth. All right, so if we call this plane W in exercise 10. So W is the set of all x, y, z such that 2x plus y plus 2x, oops, I said 3x. 2x plus y plus 3z equals 0. So that forms a plane because it has two free variables, and then the third variable is fixed based on two free ones. Then we know that R3 is going to be the direct sum of W and W perp, where W perp is the set of all V such that V dot W equals 0 for all W in capital W. So this is the set of orthogonal vectors, the set of all vectors orthogonal to every vector in W. So how do we work this? Let's see. So let W be in W. So, so W is a sum of, let's see. How do I, where do we go with this? Well, we can choose any value for x and any value for y. And then z or we could say W1, W2, and then z, or the third component, is 1/3. Well, it'll be negative 1/3 times 2W1 plus W2. Like negative 2/3 W. Z is negative 2/3 X minus 1/3 Y. Yeah. Then, and let V be in W perp, so V dot W equals 0. Therefore, V1 plus, well, you know what? I know exactly what V is. V is a vector that is orthogonal. Yeah. To a vector that is orthogonal to two three-dimensional vectors is the cross product of those two vectors. So two independent vectors in W are dude, I don't know. What letters do I want to use? W, T, U, V, maybe V and W. So if we let the first component be 1 and the second component be 0, that's saying that x is 1 and y is 0, then z is negative 2/3. Or I could rescale this, multiply everything by 3 so that we are working with whole integers. So that is one. And then another independent vector in late JC stream. Yeah. What's up in Stucky? Good to see you on Twitch. Yeah, I didn't get to stream math this morning, so I decided, screw it, I'll just study math now instead. Okay, so if W1 is 0 and W2 is 1, then then the third component, W3, is negative 1/3. I can scale that, multiply everything by 3, and then we have a nice vector to work with. 0, 3, negative 1. So those are independent. They're not themselves orthogonal. Notice that those are not orthogonal vectors themselves. But U being the cross product is orthogonal to both V and W. This is a fact about the cross product that we learned in chapter 2. Chapter 1. Maybe it was chapter 1. Chapter 1. So I remember the cross product by the 3 by 3 determinant computed like this. 3, 0, negative 2, 0, 3, negative 1. So this will be, so now I'm doing a cofactor expansion along the first row. Although I wonder if I could do a 3 by 3 determinant. Yeah, let's try this as the 3 by 3 determinant in place formula. So you can do a diagonal, like multiply along that diagonal, which is 0. Multiply along this diagonal, which is 0. And then multiply along this diagonal, which is 9k. So we're left with 9k. Then we subtract this diagonal, which is 0. Subtract this diagonal, which is then going to be positive 6i. And then add this final diagonal. Or subtract negative 3j. So that is add 3j. So this turns out to be the vector 6, 3, 9. So claim that U is orthogonal to V and U is orthogonal to W. We check that U dot V should be 0. U dot V is 3 times 6 minus 2 times 9. That is 18 minus 18, and that is 0. Check. That one worked. Now U dot W. U dot W is 6 times 0, or 0 times 6, plus 3 times 3, minus 1 times 9, and yes, that is also 0. Heck yeah. Heck yeah. So both of those worked, and the cross product works as we expected. Then W perp is the span of this vector 6, 3, 9. Now, as I wrote before, this three-dimensional space R3 is the direct sum of W and W perp. W is dimension 2, and W perp is dimension 1. R3 is dimension 3, so that is lining up the way that we would expect as well. What's up, y'all? I see we got a few people watching on YouTube. Let's go. Excuse me. Please do hit the like and subscribe, all that good stuff. It helps the channel, as you probably know. Thanks for joining. Cool. So that, now we found the orthogonal complement of this plane. So how do we express that? The orthogonal complement is the line satisfying Is it a line? Wait, 6, 3, 9. Well, one thing, because I like to clean up these sorts of things, you can factor out a 3, so the span of 6, 3, 9 is the same as the span of 2, 1, 3. And that would... How do I think of writing down what that means geometrically? I know that that should be a line. If we have a vector in that span, then it is a scaling of 2, 1, 3. How do you write that as an equation? Can you? I mean, I'd say the line spanned by the vector 2, 1, 3. But I feel like I should be able to write that as an equation, like the graph of an equation. I feel like I should be able to, but I don't know. The subspace, that in R4. Let's do it. Let's do this one as well. Because I feel like we should get like a slightly... like something that doesn't require the fact that we know that the cross product generates a third orthogonal vector. This next one we'll need to do a little more work on. So W is the span of 2, 1, 3, 4. And 1, 0, negative 2, 1. 1, 0, negative 2, 1. Let's delete. Oh, whoops. Don't delete. Cut. That's what I meant to say. Cut. And bring it down here. So we know R4 is a direct sum of W and W perp. And W is a two-dimensional subspace, so we expect that that the orthogonal complement will be a two-dimensional space as well. So let W be in W, so W is two, 1, 3, 4 plus B times 1, 0, negative 2, 1. So now we can write this as 2A plus B A 3A minus 2B 4A plus B. Then let's say that V is in the complement. So V dot W is 0, which implies that V1 times 2A plus B plus V2 times A plus V3 times 3A minus 2B plus V4 times 4A plus B, that all of this has to equal 0. Huh. Well, now we have a bunch of unknowns. We have 6 unknowns, right? We have one equation and 6 unknowns, so that's, I don't think that that's the right approach on this one. What will we do next after this? On this one, I mean, we can find I feel like there's a more systematic approach on this. If I try hard enough, one day will I be orthogonal? I don't know. I don't know if that's how that works. What's up, dude? How's it going, Leo? Why didn't it work? What? iPad Hawaii book. Okay, this thing isn't working anymore. I used to have a thing that should be. I used to have a button This button should have been putting you up on screen. I don't know why it didn't work. Oh, Luna, your butt is gross. Man said iPad Hawaii book like he is activating a sleeper agent. Oh, you're on chapter 1 of this book. You're working this book yourself. Let's go. Chris. I'm going to call you Chris. iPad Hawaii book like he is activating a sleeper agent. Yeah, that's the button. Like, if I press it once, it's supposed to go to the iPad scene. If I press it twice, it's supposed to show and hide Hawaii. It worked this time. I don't know why it didn't work before. And then if I hold it, yeah, I don't know why it wasn't working. Weird. Yeah, it's like a code word, like iPad Hawaii book. Go. You. Yeah. Oh no. Now we're on some sort of watch list. Good to see you, Leo. Bro, it's been a while. I'm forgetting. How do I do this one? So, we're supposed to find the orthogonal complement of W. Well then, I know that R4 should have a direct sum decomposition like this, so it should be the span of two separate vectors. John, why are you both saying John? What's going on? If you had 6 points placed anywhere in the real plane, then what? What happens next? Luna. I feel like I need to review this section, actually. Luna, don't scratch my iPad. I'm going to call these W1 and W2. So that W is spanned by those two. Let's let V be W perp. And this is going to be the span of two vectors, V1 and V2. Then I know V1 dot W1 is 0. V1 dot W2 is 0. V2 dot W1 is 0. And V2 dot W2 is also 0. These are all facts. Facts. Which book were you going to do in the math meetups? If we start the book that we're talking about, also, what's up, Heidi? Good to see you. Heidi is a regular from the guitar stream. If I were to start like a lecture series and we like work systematically through a book, it'll be this one, Basic Mathematics, and it's like it's like high school math, middle school and high school math written by a mathematician. Like, it's like legit, kind of, I mean, it's hard. It's like, it's not hard, but it's real math, or it's like written in the style of like a more advanced math book or something. And like, if you're learning it for fun, then maybe the fact that it's harder or like more dry is a nice thing. Like, if there's no exams associated with it, and you're trying to learn it because it's pretty, like, it is pretty. It's a Lang book. Yeah, this is Lang is intense. I've got another book or two by Serge Lang back there, and yeah, his books are pretty scary. Math is kind of like an art. It is literally an art, dude. It is literally. The other books in the back are decorative. They're all Fraleigh with different covers. Yes, that's true. Fraleigh is the only book that I have ever read in my entire life. In fact, I did all of my book reports in English class on Fraleigh. If only there was a Leo Lectures JC Practices on this subject. You could. You could, dude. Representation theory, not too far away, bro. We're gonna do 4 streams in a row next time. 4 in a row. Representation theory. Heck yeah. You know the real best math book? The Bible. Yeah, that is probably somebody has said that before, yeah. Probably. Oh, I saw Heidi once in your stream. Probably scared her away. You probably did. What were you talking about? Do you remember? Yeah, probably some like hardcore nerdy shit. Like super hardcore nerdy stuff. Well, welcome to a night stream. I might try alternating like mornings alternating guitar and math and evenings alternating guitar and math. I think that could be a cool structure. Because, like, I'm not accessible at all to the people on the West Coast. Most people on the West Coast of the U.S. So, NP completeness stuff. Okay. I mean, last few times I tuned into your stream, you're just talking about DVD bouncing logos, dude. You're just literally talking about bouncing DVDs and Subway Surfers and stuff, so... Oh, cool. Yeah. You don't understand, but it's fun to listen. Exactly, right? Like, that's the idea on this. Like, maybe not everybody understands the math, but if it's fun to listen and just see somebody geeking out about something that they're passionate about, like, that's kind of what a practice stream is about. That's really cool. That's super cool to me. Yeah. Okay, so we've got these facts that I'll know. Can we get any further from this? So if V1 is, this might be slightly cursed, but V11, V12, V13, V14, or A1, B1, C1, D1? Maybe. I'm going to go with this one, this notation. If V1 is that and V2 is similar, then V1W1 is going to be 2V11 plus V12 plus 3V13 plus 4V14. This must equal 0. And V1 dot W2. V1 W2 shows that V1 dot W2 is V11 minus 2 V13 plus V14. And now we know that both of those are equal. So from this, we can get a system of equations with two equations in 4 unknowns. So if I write out these coefficients, and we're solving systems or we're solving solutions that map to 0. So we're finding the null space of that matrix. And we can solve this with our good old, Gaussian method. I'm going to get fancy and say the null space of this matrix. I feel like I'm not working this problem the way that the section has it, but I think it'll work. All right, so first line minus the second line, 3 minus -2, 4 minus 1. This is the span of two vectors. Oh, okay. This is it. This is it right now. I don't need to take another V2. I'm already finding V2 right now. Yeah, okay. Yeah, we're pretty much right at the end of this problem now. Okay, so this is now a set of solutions with two free variables and then two dependent variables. So when the third variable is 1 and the other one is 0, like this first line says that 2v11 minus... Now I can get rid of this curse like v11 and just say 2v1 minus 2v3 plus v4 equals 0. So if v3 is 1 and v4 is 0, then v1 is 1. And v2... Well, v2... Wait. Yeah, v2 is 0. Right? Yeah, and then in this other solution, v1 will be 0, and then v2 depends on v3 and v4, so v2 is -3, right? I think that this is our solution. W perp is the span of those two vectors. Man, I feel like I'm getting like a little rustier on this topic. But we got it. I'm pretty sure. John is cooking. I finally did it. Finally got there. The DVD logo stream was a while ago. I'm sorry. I know it was a while ago. I went to Hawaii. I think that was before Hawaii, dude. I saw like a couple episodes of Better Call Saul and I didn't get into it, dude. I was really big into Breaking Bad. I enjoyed Breaking Bad a lot. But then Better Call Saul was just like, I don't know. I was like, this is lame Breaking Bad, I guess. Oh yeah, dude. How's the interview? Interview went really well, I think. I mean, I don't want to like jinx it, you know. I don't want to like shoot myself in the foot or something celebrating too early, but I think it went really well. Like I'd be surprised honestly if if I don't get an offer for this thing. I mean, it's not like an offer, like just being accepted into a thing I have to pay for. Like it's a paid training thing. Like I doubt that. I don't think that the bar is too high. I don't know. Maybe I don't know. Oh yeah, I remember that, Leo. You only did 2 months in high school. That's so crazy to me, man. Yeah. So I am teaching a high school dropout. I'm gonna start telling people that. Sorry, I know that might be offensive. I don't know. Yeah, I definitely cannot read Chinese. Chris, yeah, I don't like this idea. I will continue calling you Chris. If you change your name to non-Arabic or yeah, I don't know. Like I just non Roman letters. I mean that like you already have a lot of interesting characters in your name right now. I know, but Arabic would be the hardest. Yeah. I can't read any Chinese or Arabic at all, but I just have to be able to call you something. Yeah, why did you send all your hackers after K? Like, what was up with that? You should probably practice by teaching whatever you're currently doing right now to me until I get it. Well, Latin. That's a word that I'm looking for. That's really embarrassing. Okay, well, I'm pretty confident that we got W perp now. Funny enough, the next exercise in my representation theory book is about proving. I don't know. Yeah, it is related to this orthogonal direct sum decomposition in chapter 2 review of linear algebra. This is my next exercise. V equals wow. V equals wow. Yeah. Related to the orthogonal direct sum decomposition. Wow, okay. Wow. Yeah, this is all you need to know right now. Wow. I'm not going to start from the beginning to teach you to get where we are. I mean, I could try a little bit. All right, so Chris, you said that you are in high school, so you probably remember or know about how to plot points, right? Like Euclidean geometry or Cartesian coordinates, right? There's a point x, y right there. For any point, we can consider that as a vector being an arrow from the origin to that point. If you do, then you have an angle that's formed with the x-axis. And if you have two of them, say that this is x1, y1, and then this one is x2, y2, then you can find a third one by adding them together. This would be x1 plus x2, y1 plus y2, right? You can add any two coordinates to find a third coordinate. That's kind of step one. So those are called vectors. When you have any two vectors that have a 90-degree angle, then we say that those two vectors are orthogonal. So that's what orthogonal means. We have a property about vectors that we learned earlier in chapter 1 of this book. So this relates something called the dot product, which you might be learning about since you said that you're reading chapter 1 right now. It relates the dot product to the length of the vectors. The length is how long, literally the magnitude of those vectors, to the angle between those vectors, right? So if the two vectors are orthogonal, theta is 90 degrees, also known as pi over 2. Cosine of a right angle is 0. So then if the two vectors are orthogonal, then their dot product equals 0. And that is actually quite literally what I'm working with right now. Like, these problems are about finding orthogonal vectors, vectors that are orthogonal to both of those two four-dimensional vectors. In the beginning, there were two orthogonal vectors. One of them took a bite of an apple, and there was a talking snake or something. Okay. I heard orthogonal shapes have something to do with right angles. Yeah, orthogonality is right angles. Like, that they are... I mean, it's kind of like the beginning of it or something. And this little symbol is because it forms right angles, I think. So not wrong angles, right angles. Yes, yes. And Stucky, thank you on Twitch. I appreciate it very much. That the interview went well, right? And Stucky said, glad to hear it. Thanks. By the way, I'm on Twitch as well now, y'all. So if you prefer Twitch for some weird reason, you can. Holy, he has Twitch open. I know. Yeah, today I'm trying it. He's cheating on us. I know, sneaky. Very sneaky. Very, very sneaky. Yeah, so these problems right now, they're beginning with this property. Then if you have a subspace of a vector space, then your vector space is a direct sum of W and W perp. But this requires that your vector space is an inner product space. So we do need this property. So this is a generalization of the dot product. When he merges us with Twitch chat, it's all over. Yeah, yeah. So, yeah, you haven't gotten yet to you're a generalization of a dot product. What was I gonna say? No, it's funny. You're lashing out at Big Twitch. Oh, you recommended Schnaf. Yeah, I'm a big fan of Schnaf, dude. One of these days I'm gonna, maybe today I might raid Schnaf. We used to raid each other all the time. Years ago and during the pandemic. Happy to see that he's still at it. It's crazy. He's probably live now. Shut up. Shut up. No, I don't see him. Bash Bunny. Oh, wait, no, Schnaf is live. Look at that. Schnaf with 43. Let's go. Heck yeah. Yeah, I might raid him later. How much more time do I have? I don't have that much more time. Let's go a little further. Let's do a little bit more. All right, so the Gram-Schmidt process. I'm moving very slow today. Gram-Schmidt's process says that if you have an arbitrary basis, for a vector space, that we can apply an algorithm to convert it to an orthogonal basis. And the benefit here is that I guess a property here is that every two basis vectors, any two of them are orthogonal. And then, like, projections become much simpler, generally speaking. Gram-Schmidt, what does Al Gore have to do with this? I don't follow that one. I don't follow what you're talking about on that one. But so our vector space right now is R3. And we have our original basis 1, 1, 1, 1, 0, 1. Yeah, I might raid Schnaf today if he doesn't raid me first. We'll see what happens. I wish, dude. Algorithms. Oh God. Oh my God, dude. Thank you. At Leo Lectures. This is an algorithm. Thanks, dude. That's great. That's really great. Okay, and the Gram-Schmidt process for this is that we let V1 be equal to the original basis vector, to the first basis vector. Then V2 is going to be, I think it's the second basis vector minus the projection of V2 minus the projection of, oh yeah, all of the previous the hell is this? How does this go again? B2 minus the projection of B2 onto V1? Let me review. Dude, it's been a little bit. It's been a little bit. I think that's right. Change of coordinates. Oh, that's coordinatization. Where is it? Least squares. I mean, I have it. I have the paper book over here. I should just look at the paper book, but I want to show you all. Okay, so yes, it is AJ is fixed, and then we're taking this basis vector and then subtracting its projection from each of the previous orthogonal subspaces. Yeah. Oh, okay, and then this is v1 dot v1. Dude, okay, it's been a little bit. I had to remind myself of a couple things here. So this is not magnitude of v1, it would be magnitude of v1 squared. But it's better to write it this way. And then v3 is going to be b3 minus b3 dot v2 divided by v2 dot v2 minus b3 dot v1 divided by v1 dot v1. Okay, now we just need to calculate all these things. So therefore v1 is the same as b1, 1, 1, 1, v2, here, why don't we do this? Okay, so B2 is the second basis vector. These are B1, B2, B3. So 1, 0, 1. Minus the dot product of 1, 0, 1 with V1, which is 2. Divided by, oh, and this is, hey, Luna, get off algorithms. That's horrible. Man, that's horrible. How's it going, dude? What's up, Sai Pranav? How are you? Let's see. I gotta probably wrap this up relatively soon, everybody. But I'm having fun. V1 dot V1 is 3 times V1 So now this is going to be V2 is 1 minus 2/3, 0 minus 2/3, and 1 minus 2/3. So that is V2. Now V3 is the third basis vector 0, 1, 1 minus 0, 1, 1 dot V2. So 0, 1, 1 dot V2 is 0 minus 2/3 plus 1/3 is negative 1/3. Divided by V2 dot V2. V2 dot V2 will be 1/9 times 1 plus 4 plus 1. So this is 2/3. So that simplifies. Negative 1/3 divided by 2/3 simplifies as negative 1/2 and minus negative 1/2. These two form a positive. There we go. We have 1/2 times, vector V2, and this is vector V1. B3 dot V1 B3 dot V1 is 2. V1 dot V1 is 3. And this is multiplied by V1. Now, we're almost done. Now this is 1/6 times 1 minus 4. 6 minus 2 is 4. 4 minus 4 is 0. 6, 7. Ha! I said it. Hey, take care, man. Thanks for stopping by, Leo. Great to see you, as always, man. Thanks for stopping by, bro. 6, 4, 6, 4, 0, 6, 7, 3. So this is our third. So now these vectors are mutually orthogonal, or pairwise. Eventually every math streamer has to say it. Yeah, pretty much every day, almost. And how many math streamers are there, though? To be honest, like, be honest with yourself. How many math streamers are there out there, dude? It's not that many. But these are now pairwise orthogonal. So if I checked v1.v2 and v1.v3, hey, Luna. And v2.v3, then that's all of the combinations of these. v1.v2, let's just see it, is 1, 1, 1 dot product with v2, which is 1/3, negative 2/3, and 1/3. Hey, Luna. Keep it chilly, Luna. And if I take the dot product of these two, then I have 1/3 minus 2/3 plus 1/3. Yep, that's 0. v1.v3 is going to be this guy. Dot product with something else. This one is v2, right? So it should go there. What is v3 again? It's negative 1/2, 0. This is really cursed. Like, everything's kind of mashing together right now. But 1, 1, 1 dot negative 1/2, 0, 1/2 is negative 1/2 plus 0 plus 1/2. That is 0. So those are orthogonal, right? Both of these so far have been orthogonal, and now the last one should also, if we did everything correctly, this one should also turn out to be orthogonal, which is, I think, pretty cool. Like, since you have learned about the dot product and you've learned about the cosine factor of, or the cosine fact about vectors and their angles. So this is negative 1/6 plus 1/6, and that is 0. So now vi dot vj equals 0 for all I not equal to j. I mean, for all of the any two distinct vectors in this set are orthogonal. And now I have a three-dimensional basis, so it spans, because the dimension equals the parent space, then it spans the parent space. Now the last step in the algorithm is to take find the we need to normalize every vector. So I don't know, v1 prime or something is v1 divided by the length of v1. Which would be square root of 3. The square root of the dot product of v1 with itself. So we have 1 over root 3 times 1, 1, 1. So we normalize each. I probably should do like a star or something, not a prime. V2. I chose 1/3, negative 2/3, 1/3. We could use 1, negative 2, 1 instead. And then normalized the 1, negative 2, 1 is easier to work with instead of a bunch of fractions that we're squaring and stuff. Because you can scale vectors and they span, like any multiple of a vector still spans, is also in the span of the original vector. So if we scale this, then the dot product of it with itself is 6. So this is 1 over root 6 times 1, negative 2, 1. 1 over root 6. One, negative 2, 1. And then V3 star is going to be V3 normalized, which is similarly, we should really work with negative 1, 0, 1, which then normalizes to 1 over root 2 times negative 1, 0, 1. Same thing. 1, 0, negative 1. Cool. Now, this collection is now an orthonormal basis. Cool. I think that's pretty awesome. So starting with any arbitrary basis, we can generate a orthonormal basis from it. Neat. Now, orthogonal matrices. Let me cross out some problems so I know that we did them. Now we've got probably thousands. No, dude, I don't think that there's thousands of math streamers. Dude, I don't think so. I think there might be 100. Math streaming is a fairly niche thing. Like live streaming math, or like math creators, like math YouTubers, yeah, thousands. Streamers? I think math streaming is a fairly niche thing. I don't think that there's thousands. I think that there's less than 1,000. And I would not be surprised if there's less than 100. I haven't seen math streamers before. Like, turns out that there's a couple, but there's really not many. Exams. Yeah, well, so I mean, there's like a lot of like study with me streamers, like people who are themselves just studying, but not showing math and like teaching math or something. Okay, yeah, some instructors maybe like if you count Zoom, yeah, sure. Thousands of math teachers on Zoom, but not streaming. Like trying to build a YouTube or Twitch following as a streamer. Like I think that is very rare. Like yeah, like if we count Zoom, yeah, there's thousands or millions. But okay. In this, A and D are square matrices, D is diagonal, and AD is orthogonal, then AD inverse is AD transpose. So because AD is orthogonal, this is the definition of an orthogonal matrix. D inverse A inverse equals D transpose A transpose from the previous line. So A inverse is D transpose A transpose. D transpose is D squared. Okay. Okay, so find the matrix, the inverse of each matrix A by first finding a diagonal matrix D so that AD has column vectors of length 1, and then applying the formula. So A is that matrix. How do we... Let's see. I think that these columns are orthogonal. The column vectors are, I believe, are all orthogonal. So -2, -4, -2, 4, yeah. Yes. I believe I see that A has orthogonal column vectors. So A has orthogonal column vectors. So if D is a matrix, is a diagonal matrix, it's a scaling. Let's see. So we want AD to be orthogonal. Then AD is, this will be the last problem we work. -2, 1, 3, 1, 2, 1, -3, 1, 2, 1, 3, -1. So what does multiplying by a diagonal matrix on the right do? Does it scale the columns or the rows? I believe it scales the columns. So let's see what happens. 2... Yeah, this would be like 2d1, negative 2d1. Yeah, it scales the columns. 2d1, 2d1. So d d1 should normalize the vector 2, negative 2, 2, 2. i.e. d1 is going to be equal to, it's like the scaling factor that we need to multiply by. So it's the square root of the dot product of that vector with itself, which is going to be, so this is the same as 2 times 1, negative 1, 1, 1. The square root of 4 times 1, 2, 3, 4. So that is 4. So d is 1/4. Similarly, I think I can just write out all of them. So the first one needs to be 1/4. The second, oh, my iPad's dead. You know what? I think that that's a good sign that we should wrap this up. I think that we're done for today. iPad is dead. Y'all, I appreciate you all. Thank you for watching. Night stream was successful, I think. Thanks for watching. I gotta go. Bye. Bye. Convenient excuse, I know. But yeah, thanks for watching. Bye.